So we're gonna keep going on randomized linear algebra. And today I'll just do a little bit of board work, but mostly we're gonna spend is doing some MATLAB programming. So that's what we're gonna spend our time with this time. We're gonna actually implement this and show how it works and show how such a strategy could actually be really useful in practice for large data matrices. I thought it'd be good to review real quickly, in some sense, the sketch of how this algorithm works. The whole concept is to start with some big matrix, A. That's our big data matrix. Normally, matrices we work with, whatever size they are, but the idea here behind randomized algorithms is suppose that A is so large, whether it's because you have so many rows or so many columns that you really can't even fit it in memory. And so, but you'd still like to look for patterns. You'd still like to look for PCA analysis of this data. So you might want to do an SVD, but the SVD itself, how can you do an SVD when you can't even fit the data into memory? And not only that, you're going to require to do something like, if this was a square matrix, to be something like order m cubed operations, right? So these are really large computations using, that you'd have to do, and maybe not even possible to do because you can't fit it in memory. So how would we address this? So part of the idea here was we make a very fundamental assumption around randomized algorithms, which is what I'm really interested in here is low rank structure. So remember, this is going to be really critical. This randomized linear algebra really is all based upon the fact that I'm actually going after the fact that the column space here is spanned by some low rank representation. That's the key to making the whole thing work. And so what you're going to do is you're going to sample column space in a random way. In fact, the way we did this is we made up a matrix omega, which is n by k. So each row of this, when it hits this, these are random numbers. We're going to just make it a rand n. So we're going to make them randomly distributed, positive or negative. And what they are is going to allow me to construct a linear combination of the columns of A in some random order. Okay? And I have k of these random projections. So I'm going to go hit this matrix A and sample from the column space with k random projections. Now, if this is very large, then with high probability, each random projection that I get will be orthogonal. In other words, each time I hit this, it's kind of in an orthogonal direction. So this is nice because it allows me to sample, in some sense, with k samples, the column space of that matrix A. Now, when I multiply these, I get a new matrix, Y, which is now m by k. So k is much less than m. So the idea is that, I haven't drawn this to scale. It's not like, oh, I went half the size. Normally, this is like, maybe I have tens of millions or billions of columns, and now I shrink it down to hundreds or thousands. Okay, that's kind of the idea of what you want to do. It depends a lot on what the rank of the structure you're looking for is. And where this is going to work best is if you really have nice low rank structure. And so what we're going to do, you're obviously going to play with this in your homework, but we're also going to do it here on an example where I'm going to construct artificial data for the matrix A, which is pretty low rank. Okay. So once I get this matrix here, Y, what I'm going to do is create an orthonormal basis for the column space. And that's pretty easy to do because that's exactly what QR does. So you're going to QR decompose this. QR. Okay. So I randomly sample through random projection to this matrix, do the QR, and now this Q, what it represents Q itself has K columns, and those columns are now orthonormal. And so in some sense, this is spanning the column space of this much larger matrix A. That's the whole concept here, is by random projection, create a coordinate system which spans where my data lives. Okay. So that's step one. Step two, from that column space, is to now take your data and then look at low rank features in that column space. So the way you do this, you take that matrix Q, lay it on its side, transpose in other words, and multiply by A. So what I'm going to do now is project every column of data onto this orthonormal subspace. So originally I was living in n dimensions up here, and now I'm going to project into k dimensions. The k dimensions spanned by the columns of Q. Okay, this is going to give me a B matrix, which is k by n. Okay, now this is the matrix I'm very interested in, because what I'm going to do with this matrix is do the SVD. And I'm going to find U tilde, sigma tilde, V tilde. So in other words, I project into this space, do the SVD. I now have low rank structures. And if I want to go back into the original m-dimensional space, what I do is just take this U tilde, and U itself is equal, project back out, U tilde Q time. So I just take the U tilde, which is a low rank feature space. Remember, I projected into there with Q transpose. I just multiply by Q to get back. And those are the U. That is the randomized algorithm for the SVD. Random sample, random project into the column space. Take that column space, project your data into it. Now you have a much smaller matrix to do your SVD and work on. And the idea is that this is a manageable size. And then I can compute the SVD, find the modes, project back out through here. Okay, so that's the concept. And that's what we want to work on today. Take a data matrix and do exactly this and see how well we do. What kind of choices do you make? Well, you do have a choice about how you do your subsampling column space. And typically what people do is they'll do randomized projections or random projections, because in fact, with high probability, these are orthogonal directions. And I showed you that last time in class. Remember, I took two random vectors, and if they're big, essentially they're orthogonal to each other. Okay, so you're basically looking in orthogonal directions in this space to construct this. And so we're going to do that. And then and the choices you make here, though, is how many random projections you pick. So K is really important. Once you pick K, you're saying, I'm going to sample this. I'm going to create a subspace spanned by K directions. And typically, the way you want to do this is you want to pick K to be the rank plus a little bit of extra. And we're going to talk a little bit more about this on Wednesday, about oversampling from the rank. Suppose this thing actually had a true rank R, then you don't want to actually just take R columns. You want R plus L, and there's some reasons for that. And we'll talk about that next time in class. So that's how you want to pick K. Now notice what this does. Suppose I have a system where the rank is like, 30 or something like this. And maybe I have tens of thousands of columns. Well, then it's telling me that I can then crush those 30,000 columns down to like a matrix, which is like 40 columns. Find a 40 column subspace. Project, do my SVD, come back. And the question is, does that really work? And so we're going to try to play around with that and do this with some real data right now. Okay. All right. So I'm going to do a share screen with you. My whole desktop. There we are. And let's move back over to the driver's chair over here. I can sit down and program this for us. And I'm going to show you the data I made. And the data I made is synthetic data, of course. I mean, you could do real data if you want, but this is just so we have full control of everything. All right, so I think what you can see here is my code. And what you're seeing in the code here is I'm going to solve what's called the nonlinear Schrodinger equation. This is a partial differential equation. It's one that I've studied for a long time. Who cares? There it is. IUT plus half UXX. These are partial derivatives plus mod q squared u equals 0. This is actually going to be complex data. In fact, I'll just run this. This is some code I can share with you, but who cares? What it is what's called a soliton evolution, and I'll let you show you what it looks like. I'm just going to run it. There it is. Okay, so I start here with time 0, and here's my data. So each column, right, that's what I'm seeing here is I've got like 30 columns of, actually, how many columns of data do I have? I have only 21 slices of data. So I've saved the data 21, so this is like 21 columns. And this is the evolution of the system. So this might be something where I collect it from the bank of sensors and I measure a physical processes, and this is what I get. Okay, so that's my data. Of course, totally fabricated, not fabricated, totally synthetic. I didn't lie about this data. I made it up, but it's not fabricated. All right, so I'm gonna make this a little bit bigger. So let's make this, it's like 10, 24 points. Let's save like, I don't know, 40 slices, 41. It's going to give us 41 slices of data. I do this. Now, let me run it again. See now it takes quite a long time to run because it's got so much data there. And we'll take a look at it. There it is. Okay, so there's my data. All right. So this matrix currently is 1,024 rows by 41 columns. And we're going to change that a little bit. We're going to make it even bigger. And the question that comes up is, okay, suppose I wanted to take an SVD of this. Well, it's not that big. I could easily SVD it. In fact, let's just make sure my solution here, xsol, that's what the solution is. It's complex data, so size. Ooh. Okay, right now I have it 41 by 1024. So let's make my data matrix. Let's call it, did I actually plot this in right? I did here. Look at that. I transposed it here. I made it X. So my data matrix is X, size X. So it's 1024. That's how many rows I have by 41 columns. And what we're going to do with this is we're going to just basically, it's not that expensive to do. We're going to say, actually, let's do this for a minute here. We're going to SVD this, SVD of X, and we'll do an economy SVD, okay? Or you can do, yeah. I just want 41 principal components. And what we want to do is make a new figure. And we're going to plot here is we're going to plot the diagonals of S, okay? So plot diag of S divided by the sum of the diag of S. Okay, so it's going to give us, in some sense, the percentage of variance within each of the SVD modes. And we'll plot this with black balls of line width 2. Okay, so now I'm going to do this. I don't have to run this again. Let me just run this part, this section, one section. There's figure 2. So this is what I mean by low rank. This is the singular value spectrum. And what you see here is there's one dominant mode up here that has like 63% or so of the variance. Then you have another mode with about 33%. Then you have another mode with about 3 or 4%. Another one here. So in other words, it's dominated by 2 or 3 or 4 modes, right? From your eyeball metric that you have here. In fact, let me go ahead and not only look at on that, but let's also look at figure 3, which will be plot semi-log y and we'll plot the same thing here because we want to also look at it on a log plot so you can see how this thing looks. You run section, there's the semi-log plot. So you see it's not just 2 modes or 3 or 4, right? There's a tail here, and notice what happens. It drops off and then it goes off here. Numerical round off, by the way, well, it's down, it's down around 10 minus 14, 15. And so you see that it's full rank in some sense, but if this is on a log scale, but really the dominant modes, like the first 2 or 3 modes, okay? Now, what do they look like? Let's go plot them. So this is an analysis you might do just by looking at the system. And we're going to go ahead and plot U1 versus, I think it was, where's X? So here's the first mode, X versus the first column of U, X versus the second column of U, X versus the third column of U, and we'll do this in line with 2 to thicken it up a little bit, and make that figure 4, okay? So let's go back here. I don't like the colors when it's highlighted in there. Okay, so let's run this section. Okay, here's what those modes look like. So the blue is the first mode. You see it's nice, smooth. It's like a little bump, pulse. The red is this one here, and the orange is the third mode. So these 3 modes, how much do they take of the variance? Well, this one's sitting at around 62.4%. This one's sitting at about 33%, so 62 and 33. So you're already getting up to 95-ish percentage there, right? And this one here is about another 3.6. So now you're close to 99% of the variance is described by these 3 modes. So that's what it means to do a low rank truncation. You might say that's perfect. I'm about 99% of the variance. I capture it with those 3 modes. Those are the 3 modes I'm most interested in. And so a lot of people would say, if I SVD this data set, and of course, this is a toy data set, right? So you can't, it's got some very nice features, but if you SVD this, what you're seeing, right, is you SVD it and you find, oh, look, those are the 3 dominant modes. Almost everything you're seeing could be represented as a sum of those 3 modes. And in fact, if you were to use your SVD reconstruction, your theorem around low rank reconstructions, you would use these 3 modes, and you do a really good job at reconstructing the full dynamics that you saw, which is in figure 1 somewhere. Maybe I already killed figure 1. Oh, there, it's figure 1.
Question?
You did most of that correctly. Yes?
So we're essentially finding low rank structure in the column space. But it seems like we also have a lot of redundant information in the row space in terms of we've got a lot of zeros out in the tails. Could we, in principle, like left multiply by another random matrix to get like a good basis for the row space and then do like an extremely low rank SVD?
Well, see what happens, you see all these zeros here? That's encapsulated by these modes having all those zeros out there. So it's already got it in some sense. You see that? They're all zeros out here. So it's already saying I can reconstruct all of that because, hey, look at all the zeros I've got too. So you'd only do this SVD once through this architecture like this, right? Which would just say, find me a low rank subspace or an orthonormal set, which is right there. These 3 are going to be a dominant rank 3, R equals 3. And you can't beat that, at least from an L2 perspective. This is the best you'll ever do. By the way, you can ask, what do they look like? What's going on with those modes in time? In other words, or sorry, because this is space-time. This data set's like a space-time data set. Then what you could do is say, okay, well, let's look at this thing. Let's look at us doing T versus V. So now I'm going to look what's happening in the V, the V matrix that comes out, right? So the SVD produces U, sigma, and V. V tells you what each one of those U's are doing. Okay, so if I run this section, that's what these modes are doing. So, oops. All right. So you see the red here, or see, let's look at the blue first. You see the blue mode? Here's what it's doing in time. It's doing that oscillation. You see the red? This is what it's doing in time. See the orange? This is what it's doing in time. And by gluing those three together through linear superposition, you can basically explain that to within 99%. You're 99% accurate in a way. So that's the idea of an SVD decomposition. You see how powerful it is. So what we're going to go after here is to say, great, SVD is highlighting for you the features you should be looking at. In other words, you could take a look at this and say, yeah, it looks like there's nice structure there. What dominates the structure? These three modes. Okay. In fact, the blue one has something like 62%, right? So that's a very big dominant mode for this. Explains a lot of what's going on in there. And why? Because if you look at this picture, right, look, it's a bump in the middle. So it's not that surprising that bump would represent a lot of the variance. Okay. So now the question is, how do we get to this a little bit more cleanly or easily? I want to do this SVD. What I showed you here was, I just used this command SVD. But this is not that big a data matrix, so it's pretty easy. So what I just did is ground truthed it for you. And so now what we're going to do is we're going to start playing around with what would I do if I was going to do a randomized linear algebra algorithm here. In other words, I want to get that low rank structure, but I want to do it by using this randomization technique that we've been playing around with. Okay, so first of all, what we would do is we would construct a sampling matrix, omega. So these are random projections. And what is omega going to be? Well, it's going to be some rand n. And what are they going to be the sizes? So I'm going to take this omega and I'm going to multiply by a. So before we get too carried away, let's just do x. In fact, I have it all up here, right? N is the row space, and the total number of I save a total number of 41 data points. But what we can do is just directly find it here and just say mn is equal to size x. Okay, now let's just double check what this gives us in our command window. So m is 1024, n is 41. Those are the rows and columns. So I have those, and I'm going to use those. So now the random matrix is going to be n rows and some k. Let's call it k. And k is going to be equal, I have little k up there, so this is going to be big K, is going to be the number of random projections I pick. So let's say something like 10. We're going to break this. We're going to just say I'm going to take 10 random projections. And so this is going to be a random matrix n by k. And so what I want to do is construct this matrix Y, which is equal to A times K. Sorry, omega. Okay? So that's our... So let's run this piece of code here. So what we're doing here is our random projection to create this matrix Y, which is created from random combinations of the columns of the matrix A. Okay, and let's just do a size command here, just to verify for us that this thing should be M by K. Okay, so run section. Oops. Oh, sorry. This should be data matrix X, not A. Okay, run section. Okay, there it is. Great. So Y is equal to 1024 by 10. And I should just go ahead and hide that. And in fact, let's look at what that omega matrix looks like. So let's do a P color of omega. Oops. There it is. That's that sampling matrix. It's just random numbers. Remember, it's 10 columns. And so because I have 10 random projections, and then I have the number of columns I have is 41. And so this is what I'm basically taking this random projection matrix, multiplying by my data matrix X to produce the Y, which is right there. Okay. And now what do? So we verified that the size is right. So now what we're going to do is do a QR decomposition. So you're going to take this matrix Y, say QR is equal to QR Y. Do an economy QR. We don't want a full thing. Okay. And then what we're really interested in is looking at the Q that comes out. In fact, I guess let's make this a capital Q, because I think this is, we'll do it like that. Keep everything. So size Q. So size Q, again, should be the same size as Y, which is going to be 41, right? Sorry, it's going to now, sorry, Q is going to now be size M by K. So let's run this section. Oops. Oh, 0. I think it's 0 like that. Oops. Sorry, guys. Let's do the help QR. When in doubt. Oh, just 0, not in quotes. Sorry. Okay, there we go. All right. There we go. And there you go. There's the answer, 1024 by 10. So we now just constructed here Q, which is our column space. Okay, so this is, call it stage A. So remember, we talked before about breaking up the QR algorithm to stage A and stage B. So stage A was simply to take the data matrix, do random projection to construct a set of orthonormal vectors that span the column space of the data matrix. And that's what we just did. We did random projection, QR. There we go. We have an orthonormal set of 10 vectors that span the column space, which is 1024. That's its dimensions. The second step now is to take the matrix A and project it into this column space and then do the SVD. Okay, so what we're going to do here is to get this matrix, matrix B, what we're going to do in matrix B is we're going to say that is Q star, or Q transpose, sorry, Q transpose times A. That's what I wrote on the board. So now B is Q transpose A. So now I've just constructed this smaller matrix B that I really want. And now I want its SVD. Let's call this USV. These are all going to be caps versus down here, by the way, right? These are all small letters. The U, S, and V will be the approximation, the low rank, this randomized approximation to USV. And it's the SVD of B. And once I have that, by the way, and I want to do this, I want this to be an economy, SVD. And then I can say, oh, well, that's to get back to the actual u. Let's say this is my u approx. It's equal to q times that u. So now this gives me back my approximation to what the u would have been for the full decomposition. Okay? So that's it. Stage A, stage B. And now we get to compare these. So notice what I have here is I have some code down here, right, that I was already doing the SVD with. So now what we really want to do is come back to this code and say, oh, actually, I want to plot a few more things on here. For instance, what you'd really like to do is plot now is, let's do the following. X versus U1, and we'll make this, in fact, let's start picking out line colors. We'll make the first mode black, and then we'll make the second one, approximation, black dotted line. Okay, and then the second mode, and then the approximation to the second mode with, what color lines do we want here? How about we do this one to be red, and this one here is going to be red dotted line. And then finally the third mode, and we'll make that X, U3, and then we'll make these be, how about magenta? And this will be magenta dotted. So that is our comparison between, and we'll take away this. So stage B here, notice what we've done. We're going to do this SVD. We're going to approximate the SVD with this. And now here's my approximation. Oops. I got to, actually, this isn't U, it's U approx. And then this is U approx. And then this is, where's, oops, that should have stayed like that. This is U approx. And this is U approx. Okay, there we go. So that's what I have here. And I'm going to go ahead and take my approximation and pull out the first three columns and compare it to what you would have got from just doing a straight SVD. Okay. And if I did everything right, this will work. And if I didn't, we'll have to fix it. But let's see how I did. Okay. So let's first run this here, right? So we run that. Oop. Now I got a problem here. All right. Okay, 10, boom. I actually don't want that coming out like that. So let's see here. Size X. Okay, I have that. Sorry, I've got one missing expression here. That was fine. Anybody see a missing parentheses or an expression that was off? Now is a good time.
I think you've got a period on line 63. You've got a period instead of a comma off the screen.
Oh.
Next to the magenta, yeah.
Perfect, thank you. Yeah, the only problem with running code in sections is when you run it from the beginning, it tells you exactly where it broke. When you run it in sections, it says stuff's missing, and you're like, well, which line? All right, so we'll run this section. That section produced what we wanted, which was we started off, with the size of this thing being of size of X being MN. And so we produced that. Now we have a size Q, which is 1024 by 10. This is my orthonormal subspace. Now here in this section, I'm going to run it. Oh, doggone it. It's X. Okay, there we go, run that. All right, here we are. Look at that, it actually worked. I mean, I'm not surprised, it's just that like the chances of it working usually when you just run it is usually pretty low. And it kind of, here we go. So let's go ahead and take a look. These are my results. And what I'm going to do here is zoom in a little bit. And let's compare. Okay. So what I'm comparing is the black to this black dotted line. The magenta. So you can see these different comparisons. Maybe that's too many things to compare, but if you notice the orange one, the other orange one is flipped upside down, by the way, right? So they're off by up to a sign of plus or minus 1. So in this case, both blacks are dipping down, but you notice the reds, one red starts down, goes up, one red starts up, goes down, but they basically have about the same shape. And then by the third mode, it's actually off by a little bit. Like this is what the approximation says, and this is what it actually is doing. Okay, so this is using 10 samples out of the 41. Okay, so now what we're going to do is play around with this and break it. So we're going to come here and start saying, all right, well, let's play around with, let me just make that stage, we can run it all at once. K is the magic number, right? K is my subsampling, is my randomized subsampling. So let's ask if I go lower. Let's go 5. Already didn't do that good a job, so you can imagine this is going to really break it. So if I run this section, in fact, let me, you know what might be better for me to do is actually break this into subplots. 3, 1, 1. And what I'll do is plot the first mode, and then I'll want to just break out each mode individually because it's a lot to look at in one graphic. And I'll look at each mode individually. So I have that plot, and then let's just copy paste this, and I'll cut out what I need. And then in this last one, we're plotting the U3, so I can erase everything before the U3. There we go. And this one, I'm plotting the U2, so let's start with here, U2. And when I'm done with U2, which is right there, I can delete everything else all the way to line space. Line width, good. So there's, oh, I should have kept X, U3. Boom. And I wanted that in magenta. Okay, good. I think that works. And then here, it's the U1 stuff all the way till I get to line width. All right, so let me just rerun that. There, that's a little bit better. Okay, can you guys see all this? There you go. This is the comparison of the modes. So notice, by the way, I'm using now 5. It's still not too bad. Look how well the third mode now matches up. Here we go. So this is my random subsampling. And of course, it's random. So every time I hit go on here, I'm going to get a different result, right? And at least if these are sufficiently large matrices and you take this K sufficiently large, with high probability, everything's good. Here we go. Here's another sample. Check this out. This time when I did it, look at the results. They're dead on for the first 2 mode and off for the third. In fact, let's just verify that, because in here we can zoom in. Oops. Let's zoom in there. Oh, you see it? You see that comparison? It's incredibly accurate for the first 2 modes. That's amazing. 5 subsamples. Let's do it again. You know, I do it again, and okay, so look at this one. This is horrible now. Before it was completely on, and now look at that. This is, this is where this other one sits. You see where the mode is here? It does a terrible job approximating what this is here. Okay. So this is kind of what you get. And then as you go up, you know, and obviously you don't want that kind of variability, but let's go the other way to go to 15. And if you run this, come on. Sorry, every time I do this, when stuff's near the top of the screen, it won't let me share. Okay, here we go. So there you go. So 15 is does quite a pretty good job. And in fact, let's just see if I there we go. 15 didn't do well here. I think there's a normalization issue with that one. Oops. There you go. Okay. Anyway, this is the concept. Okay. And obviously this is not that big a matrix, and this thing is I'm just kind of toying around with it, giving you an idea of how this thing works. But this is the basic core of this algorithm. It's right there. It's just basically, you know, you random sample it, you do QR, you project the data into the QR space, you SVD it, and once you have that SVD space, you come back by multiplication with Q. So remember, this is a completely synthetic and fake example. So this example here, right, I'm obviously, it's not that big a matrix. It's 1024 by 41. And so in some sense, you know, obviously we can do the full SVD and be fine. But normally what you would be thinking about this again for is like, I have huge data. Maybe I have 10,000 rows and I have 1 million columns, right? It doesn't take much to make your computer go, you know, crash basically. So, and so the idea here is that you can say like, I still want to do an SVD with that. And so this is a way to massively subsample that column space, then still get something that's sort of a tractable size SVD, which is much easier to work with. And again, I'm going to talk about bounds and convergence bounds. This is not the best example because it's not even very big, okay? Because the bounds that you get and the convergence bounds that you get are related to the rank of the data, the size of M and N as well. So I'll kick that off until Wednesday to tell you a little bit about that. But any questions on that?